Bounded data interfaces might be a bit mysterious, but essentially you can think of them as web services. So the problem that we're interested in is the following. We have a bunch of web services that allow us to access some data. In the running example I'm going to use, we will have one directory service that allows me to get the researchers from any department of my university. So I give a department, I get all the researchers. And I have DBLP, and DBLP I see as a service to which I provide a researcher, and I get the papers written by that researcher. I have these two services, and now there's a query that I'm interested in. The query is, find me all of the papers written by researchers from my department. You can see that this query, I cannot answer it by using any individual service, but I can answer it using the two services together to get the researchers from the department, and then getting the papers written by them. So we want to study this problem in generality. So when we have services in a query, when can we answer the query using the web services? When can we rephrase the query against these services? So to make this a bit more formal, let me say what I mean by services. So I assume that I have a service schema, which is like a schema in databases, a bunch of relations with attribute names. Each service corresponds to one relation. So DBLP, for instance, here it's a relation with 3 attributes, I will say. But the difference with the traditional database setting is that I cannot access the data in the relations any way I like. There are some attributes that are special that I call the input attributes, and I can only access the data by giving values to these input attributes and getting the matching tuples as a result. I cannot get all of the papers of one given year. I can only get papers based on the author. So accessing the service looks like this. I provide a value for the input attributes. So here I provide an author name. And in return, the service gives me all of the tuples that match this value, which we call a binding. So all of the tuples that match the binding, like this. This is one part of the input to my problem, the services. The other input is the query. So I want to know of the papers written by researchers from my department. I formalize this as a conjunctive query. But of course, I'm not sure that this conjunctive query can be run directly in the schema because I don't know that it uses the input attributes correctly. So here it's trying to access DBLP, but I don't know how it's going to access it. I don't know whether it satisfies the right way to access it. This is my job to figure that out. Self-reference? Yeah, it does. Yeah. Thanks for noticing. And right. And I have a third input, which is constraints. So to be able to relate the data between the various services, I write down constraints in a logical language. So for instance, if I want to say that every researcher from a university directory is featured in DBLP, I write this down as a constraint like this. So this is just an inclusion dependency. So this is the problem, and we want to figure out whether the query can be answered on the services under these constraints. So what does it mean to have a way to answer the query in this case? This is formalized using the notion of plans. So if I stick to my example query like this, and I stick to this example schema here where I have DBLP and I have a university directory with department as the input attributes, the right way to, well, the reasonable way to answer this query using these services is to run the following plan. So the plan is going to take my department and feed this to the directory service and get out an output, which is the researchers in my department. Then it will project this on the person attribute and give the persons as input to DBLP, and get out a bunch of tuples, project them to title, and return this. So in general, what we call a monotone plan is a sequence of commands like this that make use of intermediate tables. And what the plan can do is of two kinds. Basically, it can either access services by providing bindings like here and here, and it can also evaluate monotone relational algebra queries. So here it's only doing projections, but it can do any monotone relational algebra that it likes. And we say that the plan correctly answers the query if on any database that satisfies my logical constraints, then running the plan produces a result which is the same as the result of the query on the database in the standard sense. So our job is to decide, given the constraints, schema, and query, whether there exists such a plan, and to, well, compute it if it exists. So this, this isn't the first paper to study this. You might be aware that Michael has worked extensively on this, even wrote a book about it, so on how to reformulate queries against services like this and how to find plans for various notions of constraints, so for various logical fragments to express logical constraints on my data. So then what's new? So what's new is this result-bounded part, and it's what we're doing is trying to model a constraint on practical web services that had been neglected in the previous modelization of the services. It's that when I have a web service, it will not necessarily return all of the tuples that match my access. So this is from the DBLP API documentation. If I run a query on DBLP, there is a limit on how many results I can hope to get out of it. So if I want to get the papers written by a single individual, maybe 1,000 is reasonable, even for Michael. But in general, this could be a problem, right? And this is a problem because when I do an access, I'm not necessarily getting all of the results. And worse, as I don't know how these results are chosen, I have 1,000 results. I don't know if this is all. I don't know which ones they are. Maybe the accesses are not even deterministic. And so running a plan no longer has a deterministic result. So when we have this kind of result bounds, we formalize them as part of the service schema. So I say that my DBLP service has a result bound of 1,000. It means that if I do an access, either there is less than 1,000 tuples that match, in which case I get them all, as before, or there are strictly more than 1,000, and then I get 1,000 results, but I don't know which ones, so some random subset. And well, the service is free to choose this subset in any way it likes to make my life harder, okay? And my question is, how can I reformulate a query on web services that have this kind of result bounds, and can they be used at all to answer queries while still having the same guarantees of completeness of getting the actual query result? So let me recap this problem now that we have the result bounds. The input contains the service schema with the relation names, attributes, input attributes, and optionally a result bound. So here the directory relation and DBLP with its bound, the conjunctive query like before, the constraints like before. And we want to know whether there is a monotone plan for the query on the schema under the constraints, which means that the plan should return the correct query result for every possible way that the services answers the accesses that are made. So remember that the plans are no longer deterministic because the services can decide on any subset of the right size when I make accesses. The plan is only correct if for every database that satisfies the constraint, for any way to choose results when making service calls subject to the rules, then the plan correctly answers the query. So we want to figure out whether this problem can be solved and what its complexity, depending on which language of constraints I allow for the constraint sigma here. And in a more philosophically and ill-defined way, we want to understand if these result-bounded services are of any use to answer queries in a complete way, or if the story is just that we can completely get rid of them and they're not useful at all. The summary of the results that we get from this investigation is we prove some schema simplification results that describe in which cases result-bounded services can be removed, or in which cases the result bound can be removed by rewriting the schema a bit. And we show complexity results for a bunch of logical fragments. So here's a table with all of the fragments and the results that we have. So let me go over them. We have inclusion dependencies, bounded with inclusion dependencies. So those are inclusion dependencies that export only a bounded number of variables. We have functional dependencies plus unary inclusion dependencies. We have equality-free first-order logic, and we have a subset like frontier-guarded TGDs, which has fortunately been defined just before, so I don't have to go over it again. And for each of these fragments, we show the complexity of the problem of deciding the existence of plans, and we show a simplification result that helps us get the complexity bound and which describes in which sense we can use the result-bounded methods. So in the time that remains, I'm going to explain a bit more how we get these results, and I'm going to go over the three kinds of simplifications in turn, explain what they mean, and then, yeah. So let's start with existence check simplification. The existence check simplification is the idea that if I have a result-bounded service like DBLP, so it has a result bound, if I give an input, I'm not sure I get all of the matching tuples, but if I just want to check if something is in the relation, then this is fine. I don't need to get all of the results. I just need to know if there is any tuple that matches, and this can be useful to answer a query. So consider the query asking, has Michael Benedict published anything? I run this by accessing DBLP, providing it Michael Benedict, and I check if the result is empty or not. So then the fact that there is a bound is really of no concern. I just want to know whether there is something or not, so that's fine. If the bound were 0, this wouldn't work. So we assume that, we assume that the bound is greater than 1. If we have a bound of 0, then, well, without formalization, it's not useful at all, because then it means we are never going to get any result. So if we have a bound of 1, then that's okay, because we either get nothing or we get something, and this is all we need to know. So this is one first way in which a service can be useful, even though it has a result bound, okay? And so to characterize this, like basically to describe the cases in which this is the way we can use result-bounded methods, we introduce this existence check approximation and existence check simplifiability. So let me explain. This is a property of the schema with its constraints, and I said that a schema with some constraints is existence check simplifiable if whenever a query has a plan on the schema under the constraints, then it still has a plan on the modified schema that we call the approximation. So how do we define this modified schema? We create for each result-bounded service like this a new service, which we call check, like this, DBLP check, which only has the input attributes, but no output attributes. So this service I can just use to check if something is in DBLP or not. So then, of course, I have to enforce that the semantics of DBLP check is actually what I said. I can just do this by adding inclusion dependencies to my constraints sigma. I say whenever there is something in DBLP check, then there has to be a matching tuple in DBLP, and the projection of DBLP is in DBLP check. So DBLP check actually does what I said it would. And I forbid direct accesses to DBLP. So the plans cannot access DBLP directly anymore. They can only look at DBLP through this DBLP check relation. So this basically forces them to just look at DBLP by making this existence checks that I mentioned. And then this means that the result bound on DBLP is no longer relevant because I'm no longer making any accesses on them. So in the existence check approximation, there are no result bounds anymore. And we can show that this is the only way in which result-bounded methods are useful for inclusion dependencies. So if my schema has only inclusion dependency constraints, existence check simplifiability holds. A query is answerable if and only if it is answerable in the existence check simplification. This means also that I get a complexity result for the task because I can reduce the case I can reduce the case with result bounds to the case without result bounds. So note that here I'm just adding inclusion dependencies to sigma. So if sigma consisted of inclusion dependencies, adding these constraints, I still have inclusion dependencies. I no longer have any result bounds, and so I can just apply existing results without bounds and get expand completeness. This is the first kind of simplification. Result-bounded methods I can use to check whether tuples, whether some matching tuples exist or do not exist. But this is not the only way in which I can use result-bounded methods. In the presence of different kinds of constraints, for instance, functional dependencies, I can do more. Imagine I have a service like here, dir2, that has 3 attributes, name, address, and phone, which is a directory. I can use it to give a name and get the address and phone number of that person. But people can have multiple phone numbers, but we assume they only have one address. So we have a logical constraint that tells us name determines address. I can have multiple tuples with the same person with different phone numbers, but they all have the same address. Okay? And say my query is to figure out where Michael lives. And even if Michael has a very interesting life and had like more than 1,000 phone numbers, he will still have only one address. And so I can just make my access and get the address from any return tuple, and the result bound is again no longer a problem. Getting just one result will be sufficient. I just have to look at the address, and thanks to the functional dependency, this is okay. So to capture this notion again, we introduce the FD simplification, FD simplifiability and FD approximation. It's very similar to existence check simplification. The only difference is that instead of creating a check relation that just checks for the existence of a tuple, the relation is called now FD instead of check, right? And returns a result. It returns the attributes that are determined by the input attributes. So here, dir2fd returns me the address of someone, but not the phone number, because the address is determined by the name, but the full number is not. So the output attributes are the ones that are determined by the input attributes according to sigma, according to the constraints. And again, of course, I need to add inclusion dependencies to enforce the right semantics. And again, I prohibit direct accesses to this, and I only access DR2 via this. And it turns out that for functional dependencies, this is the only thing we can do with result-bounded services. So with functional dependencies, result-bounded services, we only use them to get functionally determined parts of the input. And so again, result bounds are not a concern. They can be eliminated. There are no longer any result bounds in the FD simplification. And so we get NP completeness for checking whether there exists a plan or not for FD constraints, right? So now I come to my third kind of simplification. So these simplifications are more and more, like the simplifiability requirements are more and more, less and less strong, right? So existence check simplifiability was a very big claim saying I only use them for existence check. FD simplifiability is a bit less strong. Now choice simplifiability is going to be even less strong. If I can show, actually, in the paper, we have an example that says that FD simplifiability does not always hold, even for TGD. And the last resort that I have, the third kind of simplification, is choice simplification. We say that a schema is choice simplifiable if I can replace all result bounds by one and get the same, like the same queries are still answerable. So the choice simplification is just take the schema and replace every result bound by a result bound of one. When I have a result bound, I assume I get only one tuple, but I'm not hoping to get anything more. So this is a less strong requirement, simplifiability according to this sense, and it holds for a big class of logical constraints. It holds for all of equality-free first-order constraints. It also holds for functional dependencies because FD simplification held for them, and this is a weaker notion. So I cannot use this directly to get complexity results because I cannot decide, of course, for all of equality-free first-order logic, I cannot decide existence of plans. But if I restrict to decidable fragments of first-order logic, frontier-guarded TGDs, for instance, I can have a result saying me is 2x prime complete. I can also show the same thing. So for FD, I told you it follows from FD simplifiability. And also for FDs and unary IDs, we can show that choice simplifiability holds, and which implies decidability of our task. I haven't said much about how these results are proven. The techniques in one slide are that we simplify the axiomatization of result bounds as much as we can. First, we get rid of the non-determinism by proving that we can assume without loss of generality that making the same access multiple times will result in the same output. Then we say that we can only write the lower bound, so when we have a service with a result bound of 1,000, what's important is that if there are too many results, I get at least 1,000 out of the service, but I don't need to assert that the service will not give me more of them because this would only be useful for me, so I don't need to make this part of my logical formalization. We show that plan existence can be rephrased as answerability. This is as in prior work by Michael. We never actually manipulate plans because this would be inconvenient. We have instead an equivalent characterization saying a query is answerable if and only if when a database satisfies the query and another database has more accessible data, then it also satisfies the query. We have to twist this a bit because here it should be if there is one set of accessible data which is bigger, etc., because of the result bounds. But anyways, the simplification results themselves are shown using a blow-up argument. So we show to show that when you're answerable and you're still answerable in the simplification, we show the counterpositive. If you're not answerable in the simplification, we show that you're not answerable either on the original schema, essentially by taking a counterexample and blowing it up. So adding more things to the counterexample so that we get sufficiently many results to make it a counterexample with the larger original bounds. And the actual complexity bounds are shown by like going through answerability and rephrasing answerability as query containment under constraints. Again, this is inspired by what has been done in the setting without result bounds. By looking closely at the kind of query containment with constraints that we have and at the, depending on the logical fragment that we are dealing with, we can show the complexity bounds. The paper contains more things than I could fit in the slides. So to give you an overview, it also contains a linearization technique to get the complexity results. So this is a technique for query containment under some kinds of under a logical fragment consisting essentially of inclusion dependencies plus side information in some sense. This is how we get our complexity bounds for bounded width IDs and for UIDs and FDs. The paper also contains a result for arity2 constraints, which is an interesting setting because here we don't have any simplifiability. We're just doing the reduction to query containment and we get decidability of plan existence. The paper also contains results about when we assume that databases are finite and they cannot be infinite. Also contains a study of plans that are non-monotone, so when plans can also use non-monotone relational algebra. And we also show in the paper that for complicated first-order constraints, choice simplifiability is not the end of the story, and it doesn't always hold. So let me recap what I have told you so far, and well, this is the last slide, so all that I will tell you today. The problem that we are dealing with is given some services, given a query, given logical constraints, is there a plan or not? And we attack this in the context where we have result bounds on the services, and we show simplification results to describe when the bounds can be removed, and we give complexity results. So here is the table again of the simplification results and of the complexity results. In terms of future work, what remains would be to understand in more detail what this linearization technique can actually do. So here we use it for some specific constraint languages, but it seems like it could do more outside of the context of result-bounded methods or accesses in general. And there's also the practical question. So, of course, as Michael told us, we should think about implementations and systems and everything. And here, well, it's unclear whether all of this would matter in practice, whether you would want to take into account these result bounds when doing practical access over services. But then again, when you're doing accesses to services in practice, maybe getting complete query answers all the time is not so important, and maybe just plans that would not give you all of the results, but a large proportion of them in most cases would be enough, and we have no idea theoretically of how to handle this. So this is all I wanted to say. Thanks for listening.
It's a comment. I guess the moral is that you should stop publishing papers when you have reached 1,000 papers.
Well, as long as DBLP has this value for their bound. But, you should know that I have cheated in these examples, by the way, because I have hidden the fact that papers have multiple authors, actually, so my database schema is a bit bogus.
Check how many papers Smith has.
Well, DBLP, well, in principle, DBLP is supposed to be disambiguating between homonyms, but the API, I'm not sure. I think the API is just a search API. I just give a name, and, well, maybe there's a way to use a disambiguation, but the screenshot, I think, was from something that is just a search API. I give a name, and then I get a bunch of results out.
Just a general question about this plan generation, but are there situations where it really matters that you insist on a monotone plan or that you allow set difference in the plan?
I'm not sure of which one is the most...
Intuitively, you would be fine with using set difference in the plan.
I would agree.
Access of the services, but once you have data, you should feel free to take a set difference.
I don't know, Michael, do you have any... But But the question was, in practice, do we want to use monotone or non-monotone plans? Yes.
Maybe I can say also, there was an analogy with answering queries to GPUs. In that case, people study first the monotone, CPU. We start with queries that are monotone. So we're looking for an output that's somehow analogous with the...
Yes.
So, have you thought about going the other way around, not putting an arbitrary bound, but saying, okay, I'm doing web access, so the most expensive is the API access, the service access. So can I reformulate my query to minimize this?
So I think so Michael has this system PDQ, you know, Michael's implementation of this, I think, has a cost model where like the system tries to minimize the cost of the